Hello students and welcome back to OrganiChemVerse. In this video, we are diving into oxidizing reagents. There are two effective ways to master this concept. The first one is by the list approach. What does that mean? Memorize each oxidizing reagent given in this list with respect to their specific reaction they perform. For example, KMnO₄ can be used as a strong oxidizing reagent which can convert alcohols to carboxylic acid. Whereas K2Cr₂O₄, nothing but potassium dichromate, can be used to convert the alcohols to carbonyl compounds. PCC is a very selective oxidizing reagent. It always converts primary alcohol to aldehyde and secondary alcohol to ketone. No further oxidation when it comes to PCC. Whereas KMnO₄ and K2Cr₂O₄ can be used in different conditions. It can be used as a mild oxidizing reagent or a strong oxidizing reagent depending on the temperature and the reaction conditions like acid, base, etc. Then we have ozone. This can be reductive or oxidative ozonolysis. So you might have seen the alkenes and alkynes can be cleaved to form aldehydes, ketones, or carboxylic acid depending on the reaction condition, whether it is reductive or oxidative ozonolysis. Then we have osmium tetroxide and periodic acid. Both of them will convert the alkenes to diols. So wherein you are going to get syn diols, the orientation of the OH group will be on the same side. Then we have manganese dioxide. This is a very selective oxidizing reagent which will oxidize only allylic and benzylic alcohols. Then we have MCPBA, that is nothing but metachloroperbenzoic acid. Metachloroperbenzoic acid can be used to convert the ketones to esters. Esters upon hydrolysis will give the carboxylic acid. So what is the final reaction? We are converting ketones to carboxylic acid. Therefore, this is also considered as an oxidizing reagent. What about the selenium dioxide? It will do the allylic oxidation. So if there is an allylic carbon, that's where the oxidation will take place. Then we have Jones reagent. Jones reagent is a strong oxidizing reagent. It's primarily used in organic chemistry to convert secondary alcohols to ketones and primary alcohols to carboxylic acid. See, that is the difference between PCC and Jones reagent. In case of PCC, the primary alcohol will be converted to aldehyde, but here it will convert it to carboxylic acid. Then we have the three reagents which are used in the labs as well to identify the aldehydes, ketones, and reducing, non-reducing sugars. That is Tollens reagent, Felling solution, and Benedict solution. So these are the different oxidizing reagent with respect to what sort of reactions they are going to do. The other way of learning is, say you have hydrocarbons. That means what? Especially alkenes and alkynes. Alkanes generally will not undergo oxidation that easily. So when I say hydrocarbons, it's especially with respect to alkenes and alkynes. So we can convert these alkenes and alkynes to alcohols. So depending on whether the alcohol is primary or secondary, we can convert them to aldehydes and ketones respectively. The aldehydes and ketones can be oxidized to carboxylic acid. In some cases, it can be converted to ester, right? For example, in case of MCPBA, right? So then what sort of oxidizing reagents are we going to use? Say hydrocarbons to alcohols means mostly it's going to be ozonolysis or maybe HIO4 and OsO4, right? Say alcohols to aldehydes and ketones means what? Like PCC. We also have PDC, pyridinium dichromate. So this is one more additional oxidizing reagent you can remember. The aldehydes and ketones can be converted to carboxylic acid using the popular oxidizing reagent like KMnO₄. If it is ester, as I told earlier, MCPBA. If there are selective reaction, only then we use the selenium oxide or chromium oxide, etc. And these reagents can be used for testing them in the lab depending on the precipitate formed or depending on the change of the color in the reaction. So this is just the summary of the oxidizing reagent. Now we will solve some questions based on this to understand this in detail. Let's solve the first question based on the oxidizing reagent KMnO₄. In this question, you have to identify an alkene which upon treating with KMnO₄ in acid under heating condition. That means what? This is a harsh condition. That's why the alkene will convert to alcohol, further will oxidize to carboxylic acid and ketone. So you have to identify that alkene. But before we do this, let's understand how the alkenes will get oxidized to the corresponding ketone and carboxylic acid. For that, I'm going to take an unsymmetrical alkene like this, and when we use the same reaction conditions here, the carbon-carbon bond will get cleaved, and you see because of this hydrogen, this carbon will get completely oxidized to the corresponding carboxylic acid. What about here? It will remain as a ketone like this. So this is the reaction happening for this particular alkene. So you have to identify which of the given alkenes will undergo this kind of reaction to form the given dicarboxylic acid. You can see there is a diketone also. From the options, you can make out that the molecule is tricyclic. So you should end up with a tricyclic molecule. How to do this? One way of doing it is you can oxidize the corresponding alkene and then compare whether you are getting the same product or not. But this is time consuming as you have to do oxidation on 3 molecules. Rather, you take this molecule and do the retro method. That means what? Wherever you have oxygen, you replace there by the double bond, carbon-carbon double bond, and check if your reactant molecule will match with the options given. So how to do this? Let's check for the given product. First, you write down this 5-membered ring. Okay. And you see there is a ketone. That means what? There is a carbon-carbon double bond over here. To which carbon it must be attached? To this carbon. And then you see that this carbon must be attached to hydrogen. Why so? Because it is converted to the carboxylic acid. Then you write down this CH2 like this. The CH2 is attached to a carbon over here, which in turn attached to methyl. So this is the methyl I am writing here. And you see there is one more carbon here, right? This one is attached to this 5-membered ring like this. But you can see this is converted to ketone. That means there has to be a double bond like this. Now this must be attached to this carbon. So what I do is I'll write down one more carbon over here, which is attached to a hydrogen like this, right? Because you see this is a carboxylic acid. And then what do we have? CH2, CH2. So CH2, CH2, which in turn attached to this carbon like this. And check how many membered ring we got here. 5-membered ring, 6-membered ring. Here also 6-membered ring. Do we have any such option with 5-6-membered ring? No. We have a tricyclic molecule with 5-5-6, 5-5-6, 5-5-6. So none of these molecules are going to form the product as shown here. Hence the correct option is option D. Remember, if there is only one product, there has to be only one reactant possible. So that is why with confidence you can say none of these molecules will form the product as shown here. The next question, you need to identify the correct statements for the given sequence of reactions. First, let's find out what are the products formed in the reaction. Then we can verify the statements. The first reaction is oxidation of 1,2 diol. You can see that the HIO4 is an oxidizing reagent which will cleave the carbon-carbon bond and it will form the formaldehyde. So this will be our product P1. When P1 is treated with the Grignard reagent, phenyl magnesium bromide, the phenyl part is going to attack the carbonyl carbon and it will undergo addition. And upon hydrolysis, you can see that we are going to get the primary alcohol. So this will become CH2 and then alcohol. OH. So what will be this? This will be our product P2, benzyl alcohol. This upon treating with PCC, pyridinium chlorochromate, a mild oxidizing agent. It's very selective. That means what? It will convert alcohol to aldehyde. No further oxidation. That's why this is very important. So then what happens? We are going to get the benzaldehyde. Is this our product P3? No, because you can see that still it is undergoing reaction with the Grignard reagent, that is methyl magnesium bromide, and still it is undergoing addition reaction. So what happens now? We are going to get a secondary alcohol. So the CH3 will add here and we are going to get the secondary alcohol as shown here upon hydrolysis. And what is this? Product 3. So you can give the UPAC name for this alcohol. It is 1-phenyl ethanol. Let's find out which statement will hold good for this product P3. Compound P3 on oxidation with chromium trioxide in acid gives a compound which gives 2,4-DNP test. That means what? When this P3 is treated with chromium trioxide in acidic condition, this will oxidize product 3 to a ketone because it is a secondary alcohol. No further oxidation. Will this give 2,4-DNP test? Yes. When 2,4-dinitrophenylhydrazine is added to this, okay, because of a smaller group methyl here, not much steric hindrance, therefore it can still react with the 2,4-DNP and form a colored hydrazone. So that means what? It will give positive result for the 2,4-DNP test. Therefore, this statement is correct. Now, let's check for statement B. Compound P3 on reaction with iodine in NaOH gives yellow precipitate. Remember, iodine in sodium hydroxide is also an oxidizing agent which converts the methyl ketones to methyl alcohols to the carboxylic acid. How so? You see, the methyl will get cleaved here and this will undergo complete oxidation to form a carboxylic acid. So you are converting a secondary alcohol to carboxylic acid means what? This is oxidation. Therefore, this is an oxidizing reagent. And what happens to this? This will convert to iodoform. Iodoform is a yellow precipitate. Therefore, this statement also hold good for the compound P3. Let's check for the statement C. Compound P3 on reaction with ferric ammonium nitrate gives red coloration. Now, this ferric ammonium nitrate, popularly known as CAN, this is a yellow solution and when it is added to a secondary alcohol, it will convert to the ketone. Then what will be the change in the color? It will convert yellow color to the solution color will change from yellow to red or reddish brown color. So what does that indicate? It is an oxidizing reagent converting a secondary alcohol to ketone and it changes the color of the solution. So that's why it can be used to test the presence of the alcohols. Therefore, this will also hold good. Now let's check the statement D. Compound P3 on reaction with MnO₂ gives carboxylic acid. This is a wrong statement because MnO₂ is an oxidizing reagent which reacts with alcohols to form the aldehydes or ketones. And it is very specific to the type of alcohol. Only allylic and benzylic alcohols will be converted to aldehyde or ketone, but not carboxylic acid. Therefore, this is a wrong statement. Check for an option with A, B, C statements as correct. So you can see in option B, we have statement A, B and C. Therefore, this is the correct option. Let's find out what is the product for the given reaction. When isopropyl benzene, that is nothing but cumene, treated with potassium dichromate in acid and upon heating condition, what should be the product? This reaction condition is so harsh that not just alcohols, even the hydrocarbons will undergo oxidation. What must be the condition? there has to be one benzylic hydrogen. At least one benzylic hydrogen must be there so that it will cleave the bond here and oxidize this particular carbon to carboxylic acid. So what will be the final product here? Benzoic acid. And we have it as option A. Therefore, the final answer is A. So remember, whenever we have molecules like toluene, ethyl benzene, propyl benzene, isopropyl benzene, then they can be oxidized to the corresponding carboxylic acid. So generally it will be benzoic acid. But if there is a molecule like this, a tertiary butyl group attached to benzene, then it will not undergo oxidation because of the absence of the benzylic hydrogen. That is the specificity of this oxidizing reagent condition. Now let's see what will be the reagent used for the given conversion. So there is a benzyl alcohol converted to benzaldehyde. This is very simple. It has to be mild oxidizing reagent and it has to be selective, which is that PCC in dry dichloromethane. So this is also known as DCM. Dichloromethane is the best solvent for PCC. Therefore, the reaction condition must be as shown in option C. For the next question, we need to identify the correct structure of alkene or alkenes for the products formed upon ozonolysis. Whenever we get such questions, what we generally do is a retro method. That means with the help of the structure of the product, we try to find out the structure of the alkene. So how do we do that? Between the carbonyl carbons, right, we try to form the carbon-carbon double bond. You can count the number of carbons here. You see there are 6 carbons. That means what? The corresponding alkene must be a 6-membered alkene. But you see there is a ketone also. If there is a carbon-carbon bond between this ketone and aldehyde, it could be either a 5-membered molecule also. So it could be either 5 or a 6-membered ring. So that is the reason what we can do is, instead of finding out the structure of the reactants, let's make use of the alkenes given and then predict which of the given molecules are giving the right products. Let's take the molecule in option A. When we clip this molecule here and here, what are we going to get? Of course, this carbon will get oxidized to formaldehyde. So this part is correct. But let's check here. How to write the product? I'll give you a simple trick. You write down the carbon-carbon double bond as carbon oxygen, right? So this is the first carbon, second, third, fourth, fifth, and then sixth. Again, you oxidize it to an aldehyde because there are 2 hydrogens here. And what happens on the third carbon? Here, when it get oxidized, it's going to form a ketone. But look at this, at second position, we have ketone, right? What about here? It is at the third position. So this cannot be our alkene. Now let's check for the second molecule. Upon ozonolysis here, this will form the formaldehyde. What about here? Check now. Will this aldehyde and ketone adjacent in this molecule? Yes. Are they adjacent in this molecule? Yes. You can see that here. And count the number of carbons. So 1, 2, 3, 4, 5, 6. Yes, that is also correct. Therefore, molecule 2, upon ozonolysis, we are going to get the desired products. But let's check for 3 as well. When we do the ozonolysis of this molecule, you see this will form the formaldehyde. What about this part? Just check if aldehyde and ketone will be adjacent. Yes, that is correct. You can see that if the aldehyde is formed over here, right? So the endocyclic bond, you can call this as endocyclic because it is within the molecule, right? So you can see adjacent, it will be ketone. And how many carbons here? 1, 2, 3. So 1, 2, 3, and this will be an aldehyde. Count the number of carbons now. the position of the aldehydes and ketones. So at the second position, the ketone is there and 1 and 6 aldehyde is there. Therefore, 3 is also correct. In case of fourth molecule, you see the aldehyde is away from the ketone, so not possible. So fourth cannot be the right structure. So which two molecules will give us 2 and 3 only? Therefore, the correct answer is option C. For the next example, you have to find out the final product for the series of reactions. What is the molecule given here? It is a ketone and an alcohol. It is treated with ethylene glycol in acidic medium. What happens when a molecule is having ketone is treated with the diol? It's going to form a ketal molecule. And what will be the structure of the ketal? You can see here it's forming a cyclic ether like this because it is a vicinal diol, right? So this will be the structure. What about the alcohol? It will remain as it is. So this will be our first product. Then it is treated with Collins reagent. What is Collins reagent? Collins reagent is chromium oxide and pyridine dissolved in dichloromethane. And why do we use this? We use it to selectively oxidize primary alcohol into an aldehyde. So since it is primary alcohol, we are oxidizing this to an aldehyde. So let's write down that. So this is the carbon which will get oxidized to aldehyde. What about the ketone? It is masked or it is being protected over here. And then in the next step, what we are doing? We are treating this with the Grignard reagent. Now you see that the Grignard reagent will add to the aldehyde and it will convert this to a secondary alcohol. And upon hydrolysis, we can do this in this step itself. So upon hydrolysis, what happens? It will get deprotected. So this bond will get cleaved and we will get back our ketone. So students, remember, this is a protection, deprotection. Why are we protecting this? So that we will oxidize this to aldehyde and treat this with the Grignard reagent, right? That is our desired reaction and then deprotect this at the end. So this will be the final product. So is this the correct structure? No, this is not a ketone here, right? And what about here? The aldehyde is still as it is, so not correct. There is no alcohol here, so you can ignore this. So what is the correct structure? As shown in option D. Therefore, this is the correct answer. Let's solve the last question. The cyclopentanone is converted to a six-membered lactone. So this is a cyclic ester. And what is this reaction? It's a named reaction and we call this as Baeyer-Villiger oxidation. Which reagent we use in Baeyer-Villiger oxidation? A peracid. Peracid, especially benzoic acid. You can see that this is benzoic acid, right? If we introduce one more oxygen, you're going to form a peroxide bond here. That's why we call this as perbenzoic acid. And specifically, if we use metachloroperbenzoic acid, then we call this as MCPBA. Do we have MCPBA in the options? We don't have, but we do have a perbenzoic acid. So phenyl refers to C6H5 and there is carbon, oxygen, and since there are three oxygen, so you can write like this. It's nothing but a peracid. So peracid can also do this reaction wherein a five-membered ring. So you can see the oxygen will get inserted here to form a six-membered cyclic ester. Hence, the final answer is option B. Students, now you know how to apply the concept of oxidizing reagents on the given reactions. I have included some questions in this video to solve on your own. So please do solve them and comment your answer. And don't forget to subscribe the channel. Thank you.